For those of you that have followed the development of this curve tracer using the analog Discovery 2, this is a yet further improvement to it. I thought it might be handy to show you the state of the curve tracer before the improvement, and the improvement is to add a current mirror to the circuit in place of the 100 ohm sense resistor. For those of you that watched the previous series going back to my number 179 and then a few more recent videos, I've been using this example as a way of demonstrating how iterative improvements are the essence of good engineering. And so we've been improving this curve tracer slowly but surely, first to allow it to provide a step function, and then later to provide higher voltage for the collector. And now what we are going to do is to try to add a circuit to improve the current sensing capability, and that's where the current mirror comes in. So I will show you a little bit about current mirrors for those of you that may not be familiar with them, and then we will come back and look at the improvement. But so I'm showing you this so that you'll recall where we left off in the last video. So now let's take a look at current mirrors. Current mirrors come in a variety of forms, but they all basically do the same thing. That is, they sense a current in one path and duplicate that current in another path. They can be built with a variety of devices. Many integrated circuits today that are built with metal oxide semiconductors, MOS or MOSFETs, contain current mirrors. Their operational amplifiers are full of them because they are a very useful biasing technique. That's not what we're going to be doing here. But what we are going to be doing is reviewing first MOS current mirrors, just looking at the circuits to get a general idea of what's going on. And then we're going to look more carefully at a bipolar junction transistor current mirror. And that's what we will actually be using to try to improve the curve tracer. So MOS current mirrors, the characteristics are the device is diode connected. That is, the gate is connected to the drain. Now, it says diode connected. Of course, with an MOS device, there's really no diode involved. It really is just that the drain and the gate are connected to each other. Later, when we look at the BJT version, you'll see that it actually does make it turn it into a diode. But in an MOS device, that's just a convenient fiction, if you will. The problem with any current mirror is that it has a finite output resistance. We'd like it to be an infinite output resistance, because then the current voltage characteristic would be flat. In other words, no matter what the voltage was across the device, the current through it would be exactly the same. And you can't really achieve that, but what you can do is get as close as possible. And the best thing to do is to use matched transistors. Now, on an MOS device like an op-amp, that's pretty easy to do because it's all done on the same die. So it's exactly the same process, and even if the process varies, which those of you that know about integrated circuit manufacture, you know that you never get the same process twice. There are always slight variations from one run to the next. But each transistor on the that particular die is usually very closely matched. So that is why they tend to be used a lot with ICs. The other reason is they take up very little area. On an IC, area is the gold, and the smaller the area, the purer the gold. So they take up very little area, and they are a much better source of current for biasing. There is a little bit of a problem with all of these current mirrors. It's due to an effect called the early voltage, and early doesn't mean sooner in time. It actually refers to the person who first described this effect. What happens is, and it's often called a VA error, is what happens when the collector to emitter, or in the case of a MOS device, the drain to source voltage changes, and what that does to the characteristics of the device. In other words, the device characteristics do move around a little bit with changes in voltage across it. And that is often called the VA error. This is a figure that is almost never shown on the schematics or of the data sheets for transistors. So what about bipolar junction mirrors? Well, some of their problems are they have a non-zero base current. That can be improved by a much higher beta, because the higher the beta, the higher the ratio between the collector current and the base current, and therefore the variations in the base current don't make as big a difference with high beta, but they're still there. Similarly, the bipolar junctions also suffer from early voltage errors. That is, as VBE changes with voltage from collector to emitter, that is, the base to emitter voltage. A 2N3904 typically has a VA of around 150 volts. For most transistors, you'll find it's somewhere between 100 and 200 volts. Some are outside that range, but generally for most transistors, it's in that range. Obviously, we'd like to use matched transistors, and what we mean by that is transistors with similar current gain and with similar base to emitter voltage. We're going to talk about simple mirrors, then a version called the Widler mirror, which is actually named after the engineer that developed many of the Fairchild operational amplifiers, the 709 and the 741. Then a Wilson mirror, once again named after a engineer named Wilson. Sometimes it's called Cascode. Some people separate those, but they basically work on the same principle. So you can interchange Cascode with Wilson mirror. And then finally a combination of the Widler-Wilson. So let's take a look at some of those. Here is a basic MOS current mirror. One path is through this transistor to ground, and notice that the gate and drain are connected together, and this is what's called diode connected. Basically what happens is, because this voltage is this voltage, and because both of them are sourcing current, then this current will be equal to this current. They often call this the reference current. In our application, this is actually going to be the measured collector current of the transistor we're testing. Not this transistor, but of the one we're testing. So what we want to do is mirror the collector current that's flowing into the collector of the transistor over in this transistor, and we'll talk about why that might be advantageous a little later. This is a Wilson mirror, and basically it is a Wilson because it has this sort of cascode arrangement where, if those of you familiar with the cascode amplifier, you know that by replacing the load resistor with a transistor, you cut down on the Miller effect and some other issues. So the Wilson mirror is a better mirror in general than the basic. And this is the basic circuit. So now let's take a look at bipolar junction. At the top, you see the basic bipolar current mirror, where once again the reference current is flowing through this transistor. The collector is connected to the base, and the base of this transistor is the same as the base of this transistor. So if the base voltages are the same and the characteristics of the two transistors are closely matched, such that the base to emitter voltage is the same, what you wind up with is exactly the same current on this side as on this side. The Whittler was an improvement to the basic circuit in which a resistor is inserted here that sets the reference current, and then an emitter resistor is placed in this transistor. And the advantage of that is variations in base to emitter voltage are not as much a factor in the Whittler, because the voltage across this resistor provides effectively negative feedback. So changes in VBE do not change the current as much as otherwise. Let's take a quick look at what the effect of collector voltage is on the base to emitter voltage, and then we'll go on and take a look at the curve tracer. This is a picture taken from Wikipedia on current mirrors, and what it attempts to show is if the collector to emitter voltage is greater, in this case we have VCE1, let's say 10 volts, and then you raise that to say 20 volts with a larger collector to emitter voltage. What happens is these depletion regions, that is the regions between the base and collector, get thicker, wider if you will. Notice this is wider than that and this is wider than that. That increases the effective size of the base, and as a result the base to emitter voltage changes because of this, what I will call thicker base. Now, for those of you that have wanted me to move back into the Art of Electronics lab manual, a lot of this can be found in that manual. This is one of the pages, and notice this is figure 5S11, showing the Cascode or Wilson mirror in a 741. Up here at the top. And unfortunately, there are no lab exercises on this, and the reason is that for reasons that the author explains at the beginning of this, where it says a harder problem, and then neatly illustrated by current mirrors, early effect, when he introduces the idea of current mirrors here, he said, we concede that there's something funny about opening a section with a remark, you can skip this. Notice it says, mirrors, a topic you can skip. And so for that reason, he doesn't include any lab exercises. So those of you that are looking for another lab exercise out of this book, I've made one up combining the curve tracer with the Art of Electronics book. So let's take a look at that, and then we'll see how it performs. As you may recall, this is where we left off with the curve tracer, with the triangle input from waveform generator 2 through a filament transformer hooked up backwards to provide a 1 to 10 step up, then a diode to make sure that we don't exceed the reverse voltage capabilities of the transistor we're operating under. Waveform 1 is applying a step voltage through a 220K to the base, causing the base current to step in increments. And then we were sensing the current in this transistor through a 100 ohm resistor that you see here. the result was this family of curves that you see down in the lower right. Well, what we have done is replace that 100 ohm resistor with a current mirror. Notice now, we're still applying the steps here, we're still applying the triangle through the transformer, but instead of the collector current flowing through a resistor, the collector current flows through this transistor, which has its base connected to its collector. By the way, the reason that it's connected backwards is this is a PNP transistor, and so the current will flow with the arrow to ground through this transistor. The base is connected once again to its collector and to the base of the other transistor. The two emitters are tied together, and therefore the current out of this collector will be equal to the current out of this collector. Well, the current out of this collector is whatever's flowing through this transistor. So the current through this resistor mirrors the current through this transistor. Now, why do we do this? Well, not only do we get higher output impedance this way, in other words, we eliminate some of the effects of that finite resistor, but we also are now able to reference everything to ground. So, by doing this, we can either take the voltage directly off of here, or because we're now driving this transistor above the limits of the analog discovery, we put a 10-to-1 divider in so we can take it here at 1/10 of the value. But the important thing is the current. Now, instead of being sensed across this resistor, which causes this point to have to float, it instead is taken across this resistor. So by mirroring the current, we're able to reference everything to ground. So we get basically kill two birds with one stone. So let's see how that actually looks on the waveform software. And here is the result. You may notice that we now have a total of 10, move this out of the way, 10 base steps. On the left you see the collector current and the collector voltage displayed. The collector voltage is displayed in yellow, and notice that's the x-axis of this xy, and the collector current, which is now coming through that current mirror, is on the y-axis. Now, in this case, it's reading in millivolts, and of course you have to convert that based on the size of the resistor that you're using, and I'll show you the schematic again in a second. But before I leave this display, I would like to show you one additional change that I have made. The waveform that is sweeping the collector has been changed so that it is much more of a sawtooth and less of a triangle. You may notice that now it rises over actually 90, let's see, I have it set to 98%. So 98% of the time it rises, and then it falls in 2% of the time. That has an impact on the display. Come back up here. In that, it's hard to tell, but there actually is a retrace from here back to here. It's very faint above the top. But the reason that it's important to do that is that tends to sharpen up the trace and separate the retrace. Earlier, if you recall from some of the diagrams, there were a series of dots all over the screen here from time to time. That's actually the retrace of the sweep. So what we've done is we've cleaned that up by using a sawtooth wave. we have improved the current sense by using a current mirror. And we have produced what I think is a usable curve tracer. So let me show you the final circuit that I wound up with for those of you that might want to duplicate it. And once again, this is for an NPN transistor. If you change the voltages around, you could also do the same thing with PNP transistors, and you can, as I've pointed out in a previous video, also use this to plot the characteristics of field effect transistors as well, but I won't go into that, at least not in this video. Here is the final circuit on the breadboard, and the device under test is the transistor that you can just see back there. Let me move this wire, and you can see it back there. And then the current source, or current mirror, is made up of two 3906s here. So let me show you the final schematic and a few other changes that I made to optimize the performance. And here now is the final circuit. Once again, transformer to provide a step up from the waveform generator to give us a triangle wave and now a sawtooth wave that we can apply to the collector through this current mirror made up of two 3906 transistors, 2N3906 PNP transistors. Here is the device under test. That is a 2N3904 NPN transistor. Waveform 1 providing the base step, and I've changed the base resistor to 470K to lower the base voltage or the base current, partly because what I was actually doing is driving this transistor near its into saturation, near its the high level, and I didn't want to do that. So basically, to lower the curves so that I was getting more of a true family of curves over the operating range of this transistor rather than having the upper ones compressed, I lowered or raised this resistor to lower the base current. I also changed this. I started out with a 220 ohm resistor here. I went to 100 ohms in part so that it would be exactly comparable to the circuit I had earlier, whereas if you recall, this 100 ohm resistor was in the collector of the transistor. Now it's in the collector of the current mirror. So the current that you get for the same amount of current through this resistor, you get exactly the same display that you got earlier. So there are three improvements that have been made. One is using a sawtooth instead of a triangle for the base. I apologize. A sawtooth instead of a triangle for the collector voltage, using a lower base current, in other words, a larger base resistor, to get the transistor into more of its normal operating range. And finally, the use of a current mirror to sense the current instead of taking it across the collector resistor. It has the additional advantage of now making everything referenced to ground. So you now could use this circuit with the Analog Discovery BNC board, or with any other oscilloscope, even those that you cannot float the ground on, because you may notice now everything is referenced to ground. The X, or the X divided by 10, is referenced to ground. This waveform generator is referenced to ground. This waveform generator is also referenced to ground. In fact, there is a connection between this point and here. I don't show it, but these are actually tied together, so that all the grounds are now tied together. And you sense the voltage across this resistor to tell you how much current is flowing through the transistor because of the mirroring effect of the current mirror. So I hope this has been a useful exercise for those of you, whether you're interested in building a curve tracer or not. The point of the series of videos was more to illustrate the design process where you identify the weaknesses in your design and then you try to provide for them. Early on, we realized that one of the weaknesses of the design was the 100 ohm resistor here. We changed that to a current mirror. Previously, we had realized that we did not get enough collector voltage out of the analog discovery, so we used a transformer to give us some step up so that we could get this transistor up into the 15 or so volt range that it's designed to operate in. This transistor will operate up to 40 volts, but normally it operates off of a VCC range of 12 to 15 volts. So we wanted to be able to get to at least 15 volts here. And we were able to achieve that with a transformer. So as I usually say at the end of these videos, I hope you enjoyed it. I thank you for watching. And if anything, I hope what you have learned, if you didn't already know it, and I suspect most of you did, is engineering is a process. It's not one design. It's a process of iteratively improving your design, either because you realize there's a better way to do something or because better equipment, better components come along, and so you incorporate those into your design. So for those of you who may just be starting out, hope this is a lesson in the way to look at engineering as a process. For those of you with more experience, I hope it at least has shown you a way to make a curve tracer that is useful using the analog discovery 2. So look forward to some more videos. As I say many times, maybe not on this subject, but on some other subject. But in the meantime, I hope you'll have a nice day.